Hi Spring fans, welcome to another installment of Spring Tips. In this video, we're going to look at different patterns to help you build better edge services to be able to talk to your downstream microservices. And we're going to see three different approaches in the Spring ecosystem: Reactive Programming, Spring Cloud Gateway, and Spring GraphQL. So let's get going. First, we'll introduce two backend microservices to which we'll make connections. One is the orders microservice and the other is the customers microservice. Customers gives us access to customer data, the ID and the name, and it has an in-memory database of records there, and it's exposed over HTTP on port 8080. There's an endpoint called customers from which you can get all the customer records. No big deal. There's an orders microservice which represents all the orders associated with a given customer, and this runs on port 8181 using RSocket. So that's not HTTP, it's a different protocol, and we're going to use these from our edge service. Let's go back to the initializer, and we're going to build a brand new project using start.spring.io. I'll use the latest and greatest version of Java. We're going to call this the edge service. We're going to use Spring Boot 2.60, not because we want Spring Boot 2.60 per se, but because we want access to the Maven snapshot and milestone repositories, and that'll automatically configure it for us. We're going to go ahead and add the reactive web support, RSocket support. We're going to add Redis support. We're going to add security support, and we're going to add Spring Cloud Gateway. All right, now I'm happy with those selections. Let's hit generate, and we'll open this up in our IDE. All right, first things first, let's go to pom.xml and set this back to 2.5.4. We're going to keep the configured repositories, of course. While we're here, we'll bump this up to 17 because it's out now. It's awesome. And we want to add the GraphQL Spring Boot starter, which we'll use later. We want to comment out the Spring Security support right now. Spring Security, we don't need the Spring Security RSocket support at all, nor do we need this one. We do need Spring Boot Starter Security for HTTP, however, and we're going to comment that out as well. All right, so I think I'm happy with that. Let's go ahead and hit Maven reload. Now, let's build our code. Now, we're going to use Spring Cloud Gateway. Spring Cloud Gateway is a generic API gateway. It's a lightweight API gateway, and there are a couple ways you can use it. You can use it from property files, from YAML, or from the Java API. I'm all about that no YAML life, but I can understand why you would want to use something like the YAML configuration for DSLs, like Spring Cloud Gateway's DSL. So let's take a look at what that looks like. Let's go to this file, delete it. I'm going to create a new file called application.yaml. Okay, so let's go to application.yaml and we'll paste in an example of using Spring Cloud Gateway. We've got a very simple route here. Spring Cloud Gateway is composed of 0 to n routes that you define. They can have logical names. Each route has predicates that match incoming requests, which are going to come into this gateway node running on port 9999. It's going to match the requests that come in at /proxy having a host header of wildcard.spring.io. The double asterisks is the escape mechanism, but it's actually just one asterisk. We're going to then process the incoming request by passing it through a series of filters, of which these are just but a few. And then we're going to send it on to localhost 880, which again is where our HTTP customer service lives. So you can use this. This is already kind of an interesting project, right? We can run this and see what we get. Alrighty. Oh, it looks like I've neglected to put the Spring Cloud version back to where it would be on 2.54. Let's go back to the initializer, explore, copy and paste this, go to pom.xml, replace that, re-import, and restart. Okay, so the application's up and running. We can test it out by going to the command line. We can say the host header is hello.spring.io, going to localhost 9999 /proxy. And when we do that, we get the JSON back from the customer service, right? So that's worked, great. We can also express this configuration through properties, I told you, and the benefit of YAML and properties is that you can store this configuration not inside the jar, but externally in the Spring Cloud config server, whose definitions can then be reloaded. You can actually change things without restarting the config server The configuration, of course, lives in Git, so it's versionable, it's auditable, it's great for that kind of stuff. And you can actually force your Spring Cloud Gateway code, your service, to restart the configuration, to refresh the configuration without restarting the JVM itself. So that's really convenient. Now, I like the property file approach or the YAML file approach for this, but I also like the Java API. And the way that looks is if you just create a route locator instance. So you say route locator builder, and you build routes. So build, return, and each route has a predicate /proxy, for example, and host.wildcard.spring.io, and the route will be sent onward to something like I said earlier. It's going to be 8080, the customer's endpoint, but the customer's endpoint is the path. So I'll use the filter, and the filter will be customers, right? So there we are. There's my customer's endpoint, and that's the same thing. Now I love Spring Cloud Gateway's filters, right? This is you can actually do really amazing things. Oh, I think we've got to add the response header. So let's do that. HTTP headers dot access control origin. No big deal. But there's other ones as well. You can do a retry, for example, right? You can say I want to retry like 10 times. You can do all sorts of circuit breaking. You can do lots of things. One of my favorite is to use the rate limiter. And the way that the rate limiter works is you configure an instance of type rate limiter, which is a bean. The default implementation will store data in Redis, right? So rate limiter, and Redis is nice because it's an external data structure server, and it'll keep track of requests into your service, right? And so you can actually keep that count external to the instance. So if you deploy 10 instances of this gateway to your load balancer, they all share the same atomic number in Redis. And then so if you configure, in this case, I configured 5 requests per second, bursting up to 7. And if you exceed that, you got 5 instances of your gateway deployed across the load balancer, then each can get 1 request per second, basically, right? They don't all get 5. It's not 25. It's just 5 across all of them, which is what you want. You want that budget to apply globally. Okay, so I'm going to use the Redis rate limiter here. That's great. Redis, of course, is a key value server, so you need to specify a key resolver. The key resolver can be, anything, right? Like Maria, la chiave, right? This is from La Vita Bella with Roberto Benigni. That's fine. You can also look at the incoming request and take the principal and then map the principal to the principal name. And if the request doesn't have that, you can just return an empty one. And, that's fine. And that means that the authenticated user will get its own key. So 5 requests per user, which is fine. And that boils down to a nice, concise lambda. Or you could just use the one that we wrote, which is nice. That's very, very concise. Or you could just not specify anything and you'd get the same behavior because that's actually the default. So that works out very nice as well, right? But that does mean we need to have a principal somewhere. Who's installing that principal for us? Well, obviously Spring Security is our friend here. So we're going to bring Spring Security back in. And Spring Security, of course, handles authentication and authorization. So let's configure that here. So we'll say bean map reactive user details authentication return new map, and I'm just going to create a default user JLong, and the password will be PW, and the roles will be user and build. Okay, so there's my default authentication, and we're going to create a user as well. Security web filter chain authorization. And here, we're going to just configure how, how we limit access to certain endpoints, right? So let's create this. We'll say authorize exchange AE dot path measures proxy needs to be authenticated. Otherwise, we're going to say any exchange is going to be allowed to go through undisturbed, basically. Now, this is going to assume that they're authenticated. How are they going to authenticate? Well, they're going to use HTTP basic. So we're going to say go ahead and use that. But we don't want to have CSRF because that'll make our little demo a little bit more difficult by being more secure, which is good, but not great for my demo. So, okay, we've got authorization and authentication. Let's see if this works. All right, so it's up and running. I'm going to make the same request as last time, but it's going to fail this time, right? And the reason is because we're not authorized. You can see it says 401 unauthorized. So we want to say -u. This is HTTP basic for the username and password, and there's our data. It worked, and we can see the rate limiters kicking in. Giving us how many rate limit capacity we have, how much rate limit capacity we have left, and we can even drive this, while true, do, and then done. And before I kick that off, let's log into Redis and do flush all. Okay, so if I do keys, there's nothing there. Kick that off, and now you can see there's a rate limiter that's being a key that's being used to persist the number of requests that have been made. I Control-C that, go back here, refresh a few times, and it cleaned itself up. So the gateway is really great for this kind of stuff. Really turnkey, easy to use, really advanced functionality. Now, this is great for generic cross-cutting kind of stuff like routing, compression, security, authorization, OIDC, JOT, whatever, all that kind of stuff that you want to handle. Gateway probably can help you there. That said, one of the real major use cases for API edge services like this is adapting clients to services and vice versa, right? And Netflix was a famous example of this. As you know, they have a number of different clients. Who can't think of a client on which they can run Netflix, right? Android, iOS, iPads, your TVs, your PlayStations, your Rokus, your Xboxes, everything, right? Everything speaks Netflix these days. And they all have their own quirks, their own protocols, their own authentication, their own, payment scheme, everything, right? So Netflix maintains a bevy of different clients. And of course, this contributes to the testing burden considerably. Rather than having to adapt every single deployed microservice, no matter how homogeneous, to each client, they created a edge service. That way, that acts as an adapter. It takes data from the services and adapts it to the particulars of the client that's accessing it. This is great, especially if there's weird defects or bugs or whatever. It canonicalizes, it allows the microservices to stay the same and to be pretty homogeneous if necessary, while allowing different clients to talk to them, even if they may not be compatible with the services directly. So let's create an edge service that adapts our data rather than just acting on the payload or the envelope of the data as we do with Spring Cloud Gateway. We're going to use reactive APIs to talk to the downstream services. Right? And remember, the downstream services give us two things. It gives us a record, so customer integer ID and a string name for customers, and there's a record for orders, integer ID, integer customer ID, okay? And we want to use this CRM client to talk to those. I'm going to create endpoints to talk to the downstream HTTP service using HTTP. I'm going to use the reactive non-blocking HTTP client to talk to our HTTP customer service, and I'll use the reactive non-blocking RSocket requester to talk to our RSocket. Okay, so there we are. There's our CRM client. Let's now create some builds. Web client.builder and RSocket requester. You can see that they look pretty similar, right? The difference, of course, is that RSocket starts up, it's stateful, it's multiplex, so when it starts up, and the application starts up, and it stays connected for the life of the application. You can configure it to auto retry and all that, but the point is the ideal scenario is that it stays connected. That saves considerably on the constant network connection, ACK, handshake, all that kind of stuff. You just do it once per application. Okay, so now we've got these bits here. Let's use them to create these clients of these downstream services, okay? So let's get the customers. We'll use the HTTP client, HTTP localhost 8080/customers. I'm going to retrieve the data. It's going to be turned into a reactive stream of customers, et voila. And for orders, we want to get the orders. So get orders for integer customer ID. And here we're going to say this.rsocket.route orders.cid, where that's the customer ID, and we're going to expect to get back a stream of orders. Not bad. Good stuff. So now we have our APIs. Let's combine them, right? This is the wheelhouse reactive programming is that you can combine different APIs, you can compose them. In this case, it doesn't matter that one is RSocket and the other one is HTTP. Because we're using reactive APIs, it doesn't matter whether we're talking to Kafka or database or a REST API or RSocket or WebSockets or whatever. At the end of the day, you're just dealing with two types, Flux and Mono, both of which implement the Reactive Streams publisher interface. So this is a kind of a de facto specification, and everything stems from that. So you can pass around references to publishers. Now I'm assuming, I'm taking on good faith that these servers will never go down. But of course that's not going to always be true, is it? So the nice thing about Reactor, or this library that implements these Reactive Stream specs, is that there's good support for handling exceptions. I can say, let's return an empty stream if there's an error. I can say I want to retry, or I want to retry 10 times, or I want to retry with a back off, attempting it 10 different times and waiting longer for each retry. I can do timeouts, of course. I can say, let's wait 1 second, all sorts of things. And these are Reactor APIs, not web client or RSocket or whatever. These are not part of the protocols I'm speaking. These are just part of being reactive. And so I can do that for both calls, and it's the same exact code, right? So that's very, very powerful. But now I want to build, like I say, a composite. I want to compose these streams of data. So I'm going to create a new aggregate here, customer orders, and it'll be a customer on the left. The first field is a customer, and then a list of orders on the right. All right, so there's my aggregate. It's customer orders, and I want to create a new endpoint that returns both the customers and the orders for those customers, right? So get customer orders, return this.customers.flatMap. And what I want to do is, given a customer, this C, customer, given a customer, I want to store both in memory. And so I'm going to use a tuple. A tuple is like an array where each element has a type, and the element on the left is going to be a reactive stream for the customer, and the element on the right will be the reactive stream representing the orders. So I'll say get orders for customer.id, and I want to collect that stream of orders into a list. So now I've got two reactive streams, one on the left representing the customer, and then one on the right representing the list of orders. I can say, give me T1, that's the customer, give me T2, that's the orders. Let's create a new customer orders object, tuple.T1, tuple.get T2, and voila. Right? Just like that, I've made a call. And again, this is an N+1 thing. I'm making a call to both services at the same time. I'm calling the customer's endpoint, getting all the customers back, but then for each customer that I have, I'm getting all the orders. But the nice thing is that I'm using reactive APIs. So it's not doing this in a serial way, it's doing it concurrently, right? It's very, very powerful this way. And so I'm not waiting any longer than the cost of calling the orders endpoint once, basically. Now I've got my customer orders endpoint. Let's go ahead and create a controller, a CRM client REST controller, to prove that that's working. And I'm going to use my CRM here. Okay, and we'll just say inject, return this.crm.get custom orders. I'll go ahead and restart. Okay, localhost, COs, and voila, it's worked. There's our customer data and our order data, each one of them nicely stacked, together next to each other. So I have access to both in my API. The composition requires calling two different APIs. I'm in a much better position. The composition requires calling two APIs. I'm in a much better position to do that on the server side than the client would be, especially Android or iOS clients where they're going through tunnels and losing bandwidth and all that stuff. Imagine your client calls the customer API and then has to call the other one. Well, first of all, that means that the client now needs to speak both HTTP and RSocket. But second of all, it also means that the client has to authenticate twice. And third of all, it means it has to get the data and do this orchestration on the client. We can do all of that centrally using this API gateway and the API adapter. Now, I like this. We've created a view of the data specific for a particular client, and it wasn't that bad. Reactive programming makes doing the right thing concurrently as trivial as possible. And obviously, I'm using Java, which is nice and concise. But if you're using Kotlin, this gets even more concise. If you're using Java, it's even more concise. So it wasn't a lot of code. It wasn't hard to understand because we're using reactive APIs. So even though it's a simple thing, it's also the most performant thing. It's rare when you can have both, but we do here, right? That said, you're going to find you have to do this a lot, right? If you have different clients, you're going to end up creating different edge services for each client. And that's only for the moment, right? I mean, even the most sort of conservative of organization is going to have to create a browser-based HTML client, a Android client, and an iOS client. That's just part and parcel of doing business in today's world, right? At the very least, goodness knows what tomorrow holds, but there's all sorts of unique opportunities, and you want to be able to meet those new opportunities. But if part of that means adding a new API on the server side, then things slow down, don't they? So what we want is to have the data that we want, when we want it, in the shape that we want it. And there's a bit of a tension here because we have different microservices, each of which has data in its own shape, and we want this shape to look like what the client wants. So it's very tempting to just say, well, let's just put together a bunch of edge services to accommodate these clients. And that's certainly an option. It's what Netflix did in the beginning. That's part of the reason that they got so good at gateways, right? Just why they created the Zool gateway. And, there's certainly some value in that. But at some point, I imagine you just got to get tired of having to constantly adapt downstream services to be and look like one cohesive whole for the clients. And again, one of the reasons you do this, one of the reasons you make a new endpoint that just composes these other endpoints is for practical reasons like latency, like security. Right? You want to have all the security in one place instead of having to duplicate it across different microservices. But eventually, if you start doing this just because the data shape isn't right, that I think would get old pretty quickly. So there's a tension here. One, you want the data in one place. You want it to look and feel like it's one cohesive whole. On the other, you don't want to give up the isolation and ease of deployment and the evolutionary benefits that you get by using microservices. And so this is the same problem that Facebook experienced back in 2012 when they created GraphQL. They open sourced that in 2015, and of course there's a GraphQL Java project which is well maintained, well liked, and so on. And so the Spring team worked with the GraphQL Java team to build the Spring GraphQL project, which is as yet experimental, it's not yet GA. But we can easily use it, and it's building on a very rich, robust layer of code. So we'll use Spring GraphQL, which is, as I say, a milestone, to integrate our types, to integrate our APIs. Here you have three concepts: queries, which are reads; mutations, which are updates; and subscriptions, which are sort of like queries that last a long time, that could go on forever, or that could go on for indeterminate amount of time. So you describe your types in terms of a schema, which lives, in our case, in the GraphQL folder. So we're going to create a new file here called schema.graphqls. So we have our schema. At the root of the schema is a type called query. Now this is a sort of well-known type that you have to create. It's every project will have type query somewhere, and queries, or types rather, have fields. In this case, we're going to have a field to list all the customers. A single customer would be signaled thusly, but multiple customers are wrapped in a bracket. We can define the customer as well. The customer has an ID and a name. And we want it to reference conceptually. I want all the orders to be available there as well. So I'll create another type called order. And again, before we created it as sort of, customers and orders are separate fields or separate endpoints that you could call. We're going to create the type order, give it an ID field. I'm going to give it a customer ID field, right? And that's it, customer, order. These are our two relationships, our two types. We could also have another field here called orders. There's nothing stopping us. I just think that realistically for my first cut, even though I've got two different microservices, I'd like people to be able to get the customer data back with the orders data in there, okay? So let's do that. Now, this is a query, but again, you could have two other types of data. You could have subscriptions and mutations, right? And your query is going to have parameters. You can say orders by customer ID, right? And then that would give you a list of orders, right? And that's a query that takes a parameter called customer ID. But you're specifying all this up front, so it's very clear what's accepted, what's expected, what's returned, etc. And the same, the approach is basically the same for mutations. You could have a update order ID ID or whatever, right? Name, string, and then this would return a customer, right? And you could then update that. So let's go ahead and implement our query. Our query is going to live in a controller. So at controller, class CRM, GraphQL controller, and we're going to create a query mapping, which requires the Spring GraphQL project. So we'll go back to our build, make sure it's re-imported. Okay, and the query mapping is going to give us all of the customers. Okay, and for now, we'll just return empty. We're going to inject our CRM, which has served us well. All right. So we'll say, turn this.crm.get customers. Great, so that'll work. This query mapping annotation is a convention, right? It's a way of saying that we want to return a field called customers from the, it's a resolver. This method, this controller handler method, is a resolver for the field called customers in the query type, query mapping. And if you look at this, this is actually a specialization of schema mapping, kind of like the relationship between get mapping and request mapping in Spring MVC and Spring WebFlex. And actually, we need to use schema mapping here for the orders data. So we said that the customer data will come back from the customer's field. Well, we said we want to get the orders for a given customer. And in order to do that, we need a reference to the root customer. So Spring GraphQL will give us a pointer to that. And we're going to use that to resolve this.crm.get orders for customer.id. And there we go. So the field is called orders. The type is called customer. And again, we could have, this one here could have been, it could have been this. I could have been saying this, and that's functionally exactly the same thing, right? So localhost GraphQL, we get this nice shell that gets populated for you by the Spring Boot starter. And by the way, this is the same one that SpaceX uses, right? It's actually very popular, very, very familiar. You can actually interrogate all the different queries from the SpaceX organization and all their subtypes and all that. And so that's what we're doing here. We have the same thing. So we want to read the data and we want to ask for the customers. Well, the customers are in turn composed of subfields, ID and name and orders. So we need to specify, we need to pull out which ones we want. So here, I want to get the ID. Okay. I also want to get the name. All right. I also want to get the orders, right? Well, the orders themselves are a complex object and they have subfields as well. So we need to say we want ID. What else can we do? We can get customer ID. Great. Look at that. So I got the ID, the name, and the orders. If I don't want the orders, I don't pay the cost for them. I don't have to make that call to the order service, right? Behind the scenes, you know that there are two different microservices here. I'm fanning out the requests across different nodes, getting the data concurrently, right? I'm not wasting time. Not bad, huh? You can ask for what you want, you get what you want, and nothing extra. You don't have to waste time, rebuilding the new API if you don't need it. And the server isn't going to evaluate the orders calls. It's not going to call the order service if you don't ask for the order data, right? Very, very powerful. Okay, this is one of the reasons that people love GraphQL, is because it's as easy as this. And when you use a GraphQL client, you can connect over different protocols too. We're using HTTP, but you can also use the WebSocket endpoint. Spring Boot has support for that as well. In which case, your JavaScript code would just talk to the GraphQL WebSocket endpoint, which gets automatically created for you. And you send queries. You send literally multi-line queries like this, multi-line strings that have this exact payload, this JSON, not JSON, this schema, this query type in there. You just send that, and it doesn't matter if you're asking for just the customer's data and there's only 10 customers, you'll get that. If you are going to call a subscription endpoint and you're going to have an ongoing stream of records, then your JavaScript code will just keep getting callbacks until you disconnect, right? Or if you're doing a mutation, it'll send the data to the server and then give you the result, and then you're done, right? So it's just very straightforward. All right, I hope you got something out of this. I hope you learned something. Obviously, we've only just begun to scratch the surface. There's a lot of potential here, I think you'll agree, that's just waiting for you to take advantage of. These are all small, easy things you can do to build better API gateways and edge services and API adapters to help you connect your services to your clients, which are, after all, the very last step between you and their customers, right? If you can get the clients right and get those into your customers' hands, they're happy. That's the ball game. Everything's good after that. So good luck. Enjoy your journey to production. And as always, we'll